Good afternoon. My name is Matthew Appler. I am an undergraduate of Coe College, and today I'm talking about autonomous blind robotic mapping. The authors of this paper included Matthew Appler and Stephen Hughes. Now we know it is possible to explore any map. However, if the contents and size of the map are unknown, the problem becomes more interesting in trying to find an effective search order. This is even more important when we try to introduce more than one explorer. Our objectives included exploring an unknown environment using both blind single and pairs of explorers. The explorers were blinded, so they only knew if a tile was open or closed by trying to move to it. We also compared the search orders to see if they played an important role in whether or not an explorer succeeded. A search order is simply the order in which an explorer tries to move when trying to map a maze. We compared these search orders to a baseline that we defined as random movement. This is where in every movement phase, the direction that the explorer tries to move first is randomized. Finally, we compared non-sharing versus sharing to see if sharing information between pairs of explorers made the exploration more successful. The applications include exploration of any environment. These include the sea floor, other planets, search and rescue operations, ant colonies, the use in robotic vacuums, and sea trash collectors. Starting with the basics, we have the explorer. The explorer is given three things. These include a search order, a starting location within the maze, and an empty two-dimensional ray, which represents the maze that it uses to keep track of where it's been and what it's discovered. When an explorer has finished mapping a maze, it gives back an efficiency based on the average fraction of unknown tiles discovered per unit moved. This is done by taking the total number of open tiles divided by the total amount of units moved. An explorer can move in 8 different directions. These include both orthogonal and diagonal movement. If the explorer moves orthogonally, it has a cost of 1 unit. If it moves diagonally, it has a cost of square root of 2 units. If the explorer tries moving and hits an obstacle, the cost is 0 units. This is because the tile that the explorer is in can be seen as the same size as the explorer. Finally, if the explorer reaches an area where it's surrounded by obstacles and/or spots it's already visited, it will start to backtrack. The explorer backtracks by using a stack which has every location that the explorer has been before. Before it starts to backtrack, it runs an algorithm to optimize its path back to the starting location, and once optimized, it pops the top spot off and it moves there. It does this until it reaches an area where there are open tiles it can move to. 2 more assumptions made where we allowed the explorer to move diagonally even if orthogonal options were blocked. So in the picture on the right, if there was an obstacle in the direction of 1 and 4, the explorer could move in the direction 2. Secondly, we allowed explorers to occupy the same tile. Looking at the image on the right, we can see an example of a search order depicted by the orange arrows. The search order depicted is 0, 1, 3, 5, 2, 4, 6, 7. To create the unknown environment that the explorer would be mapping, the algorithm was given 4 values. These included the rows, columns, percent difficulty, and starting location. In the image on the right, the number of rows and columns was 10, the percent difficulty, which is the fraction of obstacles compared to total tiles, was 25%, and the starting location was the top left corner. To create a map, obstacles are randomly placed within an empty maze until the required number of obstacles are met. Then an algorithm is run to see if all open tiles are connected orthogonally and/or diagonally. If they are not connected, the maze is discarded. This is because an open tile that is blocked off by obstacles could be effectively counted as an obstacle, thus changing the percent difficulty. Finally, the program continues to make sure that maps are not duplicates of each other when making a set of maps. To conduct our single explorer testing, we created an environment that was 20 by 20 tiles, ranging from 5 to 60% difficulty with steps of 5%, and all explorers starting in the top left corner. We then ran all 8 factorial or 40,320 different search orders. These search orders' efficiencies were then compared to a random baseline to see which one performed better. However, there will be error in the results due to the fact that we were unable to run explorers through every possible map in a 20 by 20 environment. To try and reduce this error, we used complement explorers. A complement explorer is where 2 search orders will have the same efficiency if they run through every single possible map. When explorers start in the top left corner, we can find their complement by reflecting the search order over the orange line in the image on the right. For example, if the original search order was 0, 1, 3, 2, 5, 4, 6, 7, its complement would be 0, 3, 1, 5, 2, 6, 4, 7. By running all explorers through, pairing them up with their complements, and finding the difference in their efficiency, we can find the max difference. Taking this max difference and multiplying it by 2, we can subtract it from the efficiency of the best runner to find the cutoff. If both explorer strategies within a pair performed worse than the cutoff, they were removed from the list of explorers to be tested. This process was then repeated with a larger selection of maps and continued until we found the best search order within the error range. For our single explorer results, search orders starting with 310 and 130 performed best. This was because they prioritized orthogonal movement, which has a cost of 1 unit, before they moved diagonally, which had a cost of square root of 2 units. Secondly, they searched in the starting area before moving farther out. This reduced the chances that they would miss a tile in the starting area and be unable to get to it without backtracking. Finally, percent obstacles had a direct impact on the overall performance of the explorers. This can be seen in the example on the right. So, in the example on the right, we have the best search order, which was 310-65427, represented by the blue line, with the baseline, which is random movement, represented by the orange line. We can see that at 5%, the best search order performed much better than the random baseline. But as we increased the percent difficulty, they started to converge, with the rigid backtracking single explorer having almost the exact same efficiency as the random at 60%. This is because we reduced the areas that were large into narrow tunnels where the explorer really only had one direction to go, so it didn't matter what search order it had. This was seen for all search orders, with the majority of them doing better than the random backtracking and more of them performing worse as we increased the percent difficulty. For our explorer pair testing, we ran them on an unknown environment that was again 20 by 20 tiles that ranged from 5 to 60% difficulty, with explorers starting in the top left corner. Since we no longer had explorer complements, we ran the explorers on a selection of 500 maps per test. Furthermore, since we were unable to check all combinations of explorers, we created generalized strategies. These strategies included reflected and clockwise, where the explorers were non-sharing, and then rigid shared paired, where the explorers shared information as they mapped the environment. These were then compared to 2 random baselines. One was non-shared random and one was shared random. To create a reflected explorer pair, you'd first take your original search order and then, much like when creating a complement, reflect it over a line described by the 2 numbers in the name. So for 07, the line would be drawn from 0 to 7, and we take the original search order and reflect it over. This would also work with the 1 to 6, the 2 5, and the 3 4. The results of the reflected explorers suggested that as you increase the percent difficulty, the best search order changes, with 3-4 having the best order at 5 and 30 to 45% difficulty, 1-6 having the best from 50 to 60%, and 0-7 the best from 10 to 25%. To create a rotated explorer, you take the original strategy and rotate it using the image on the top right by the degree in the name. For example, a search order that started with 0, rotated 90 degrees, would now start with 2. In the figure on the right, we can see 180 degree rotated explorers did much better than the other strategies. This was because the two explorers would go to opposite ends of the maps and slowly work towards the center, reducing the amount of time that the explorers were exploring tiles that the other explorer already mapped. A second thing to note is that there was similar results for 45 and 15, 90 and 270, and then 135 and 225. This was because the same search orders could be generated for each pair. This can be seen in the table below, where the 45 degrees and the 315 degrees had the exact same search orders for the best pair. Finally, we have random baselines and rigid shared pair. To create the random baselines, we had two pairs, one in which the random explorers shared information and one in which they didn't. The one in which they didn't was compared to the previous explorers, while the one that shared was compared to the rigid shared pair. To create the rigid shared pair, we would take the original search order and we duplicate it. So we'd have two search orders that were the exact same, and then we allowed them to share, because if they didn't, the amount of units moved would be exactly double what the single explorer was, because they would take the same path. If we look at the figure on the right, we can see that the random shared did much better than the non-shared. Furthermore, much like in the single explorer example, our rigid paired shared performed better than a random shared at lower percent difficulties, and they converged as we got to higher, with the exception that at 60%, the rigid shared paired actually dipped below the random shared. If we take the best strategy from each category and compare them to the random baselines, we can see that the strategies perform much better at lower percent difficulties and converged much like the singular explorer once we got to higher and higher percents. It should be noted that even at 60% difficulty, the 3-4 reflected and 180 degree rotated explorers were still performing significantly better than the random non-shared baseline. Our ongoing and future work include increasing the map test size for explorer pairs to further reduce error, to expand the range of testing past 60% difficulty to see whether or not the efficiencies continue to converge, to further investigate the pros and cons of sharing between explorers by creating more strategies that have sharing counterparts, to create contextualized individual and double explorer strategies. These could include always turn left when reaching an obstacle, or always go straight. And finally, creating complex multi-explorer strategies which include more than two explorers. Finally, we wish to thank the Cole College Mathematics and Computer Science Department for funding and supporting this research. Thank you, and have a good day.